What's up guys, it's Reese here and welcome back to my channel. Today we're going to be talking about nuclear chemistry, specifically radioactive decay and half-life. It's super interesting, there's a lot of math involved, but it's totally doable. I'll break it down, show you how to solve a problem and how to apply it to real life. Let's go. Okay, so what exactly is radioactive decay? It's when unstable atoms break down and release energy or particles to become more stable. The key concept is half-life. Half-life is the time it takes for half the radioactive substance to decay. For example, hydrogen-3 has a half-life of 12.27 years. So after 12.27 years, half of it will be gone or decayed. Okay, so now we're gonna try an example problem and let's work through this together. So let's say you have 100 grams of hydrogen-3 bond. How much is going to be left after 24.5 years? So we'll have to use half-life obviously in this. And so what is the equation for half-life? Okay, so first we have to find the half-life. So half-life would just be, it's pretty simple, T 1/2. So the time times 1/2, which just means divide by 2. So we have 24.54, so divided by 2, that's 12.27. 24.54 divided by 12.27 equals 2, right? So that's 2 half-lives. So now we have to get mass involved because there's grams, so grams equals mass. So the equation for that would be M equals Mi times 1/2 N. Put it on the screen right here, you can clearly see it. So it may seem complicated, but you have your original, you have mass, you're finding the mass final, right? So mass final will be on this side of the equation. So then you have the equal sign, Mi. What is Mi? The mass initial. What's the mass initial in this equation? 100 grams. So 100 grams times 1/2 N. 1/2 N is the equation that you have to input for the half. So the number of half-life would equal to N. In other cases, N is X. I actually prefer the way that 1/2 parentheses X. So then what would the equation be as you input all the numbers that we have? So M would equal 100 grams times 1/2 to the second power. 1/2 to the second power, you can easily do that in your head. 1/4. So most of the half-life and the nuclear chemistry, like at its basic level, you don't even have to use logs or logarithms. You don't have to use any of that. You can just use like, okay, looking at it like that, what makes the most sense? 1/2 times 1/2, what is that? 1/4. You don't even have to like write anything down. It's like based on your own knowledge of basic algebra, you can easily figure out the math in this for half-life specifically. So then you do 100 times 1/4. And 100 times 1/4, 100 divided by 4 is 25 grams. So the amount left after the 24.54 years is going to be 25 grams of hydrogen-3. So super like standard, easy. It may seem like, oh, nuclear chemistry, which it is a hard topic, but like the math would be pretty basic. But in more advanced questions, you'll have the Mi, or you'll have M over Mi, M over M, just different things. But you have to remember the M is either going to be equal to MF or Mi, and most of the time it's MF. So MF, mass final over mass initial, that's one way to find the half-life. There's a lot of like thought into it, but you just have to memorize the equations, and I'm pretty sure you'll get it really easily. So there's pretty standard ways to track decay, like 25 over 100 would be a standard way to track decay. I mean, if you think about what applies to the real world and certain chemistry and certain elements that you use in the real world, you can think of smoke detectors. Smoke detectors use americium-241, which, I mean, when you think of decay, I feel like you think of decay fastly, but we have elements in the atmosphere like carbon-14. We have elements in the atmosphere like carbon-14. Carbon-14 is slowly decaying over time, but we don't even notice. Or like americium that we use in our smoke detectors. I have a smoke detector right up there. It's like it's not decaying as rapidly as you would think. That's why you can use it for such a long time. Obviously we have batteries, but the fact that you're using an alpha rays are like the lowest point on the scale. You have alpha, beta, gamma, and so you have alpha. The reason you use it in smoke detectors is because you have this like layer of like, okay, I'm only tracking alpha, and then right when the smoke comes out, that completely cuts off all the alpha. So now now like the smoke detector is going to go off because it's like, hey, like there's something in front of me. So you have radiation coming into it, which is more nuclear side, and then we have the half-life and the radioactive decay side of it, where it's like, okay, I'm slowly decaying over time. The element that's used in it is slowly decaying over time, but the radiation is the one that's blocking it. So it all works together like in perfect harmony. So it's kind of crazy when you think about it. So I actually have an experiment that you can do at home. I actually have paper clips here, and I'll probably make a video on each separate experiment. Specifically for nuclear chemistry, it's probably going to be specifically half-life, radioactive decay, that sort of deal. To do this specific experiment, you can grab a bunch of paper clips. You can do 50, I have 100. Each paper clip is a reactive atom, so this would be a reactive atom. Then you would shake them in a cup and dump them out. Remove any paper clips that are, open in a certain way or facing a certain way. Like you could choose they're facing this way or they're facing this way. And whichever ones are doing that, then you take it out and you continue to do it and you see how many are left. You could probably do it for about 3 or 4 rounds and then get your answer. So when you're doing this, if you break it down into specifically what we're learning, every time you shake a cup, that would be a half-life, right? Because you're getting like half the amount of paper clips that you were originally. And then you can graph how many are left. So you obviously want to make sure that you're graphing your data correctly, and then you can see your answer. And that's how half-life works. It's super simple. Like you shake it, take it out, and then it's like, okay, how many are left? And then you graph for each one. That's the half-life of paper clips, or whatever. You can think of it however you want. But anyways, that's the deal with radioactive decay and half-life. It's all about how atoms change, and with a little simple math, you can see how they do it. From, curing cancer to finding dinosaur bones and dating them. It's super awesome stuff, and it's super handy in the real world. If you enjoyed this video, make sure to hit that like button and subscribe to my channel for more science videos. Thank you.